This is an intriguing exercise about the Neumann functions. So remember the Neumann functions, we introduced them as a second linearly independent set of solutions to the Bessel differential equation. Linearly independent from the first solutions, the Bessel functions. Now we also have mentioned in the textbook that these Neumann functions, so y of order nu of x, that we can actually write them as follows, as cosine of nu pi Bessel function of order nu minus j minus nu of x, and then dividing that whole thing by sinus sine nu pi. Okay, so this is apparently true, but if this is true, this is rather strange, because it seems now that we've defined the y functions as a linear combination of the j functions. Just this is a linear combination because, okay, cosine and sine, they might look nonlinear, but these are just constant terms, right, for a given value of nu. So if we've defined the y functions as a linear combination of the j functions, apparently, how can it then still be the case that they're linearly independent? So what on earth is going on here? And more specifically, let's have a look at the situation where the order here, nu, is an integer value. So pause the video and think about what's really going on here. Let's have a look at what happens when nu is an integer. So we have yn of x, and then we have the cosine of an integer multiple of pi. Now, an integer multiple of pi, if we take the cosine, that will either give us plus or minus 1. So it'll be some sort of power of minus 1. That's the result. Let's have a look when n is equal to 1. So then we have the cosine of pi. So the cosine of pi is minus 1. So we should have minus 1 to the power of n, because if we replace n by 1, we do indeed get minus 1. So the cosine becomes minus 1 to the power of n. Then we have jn of x. And then we have minus, and then a Bessel function of a negative order. Now we know what the relationship is between negative orders and positive orders of Bessel functions. In a previous exercise, we've shown that this is just minus 1 to the power of n jn of x. Good. Let's barrel on and let's have a look at the denominator here. The denominator is the sine of an integer multiple of pi. Now, an integer multiple of pi, if we take the sine, that will give us 0. But here we seem to be dividing by 0, but also the numerator is 0. So this is actually 0 divided by 0. So the main message here is that this looks like a simple linear combination, but it actually is not, because it's something that needs to be evaluated in the limit. It's 0 divided by 0. So it's a whole lot more complicated than something which just looks like a linear combination. And this also explains why you can have, for example, that singularity at the origin of our Neumann function. So don't draw the conclusion that apparently the y functions are linear combinations of the j functions, because that's simply not true.